let us proceed. Phreatic line and earthen dams. I think this is very important just to avoid piping or seepage failure. So phreatic line or seepage line or saturation line is the line at the upper surface of seepage flow at which the pressure is atmospheric. So pressure will be atmospheric at the seepage line. So you can see this is the phreatic line. Just if you have water level here, then you have this is just theoretical seepage flow, but the actual seepage line is 0.3 L, 0.3 times L. L is just from this initiation point of seepage or phreatic line up to this one, just up to the heel of the dam. This is L dimension, so 0.3 L. It starts, it will join to this direction, then it will hit this blanket or horizontal filter. So you put this drainage blanket or horizontal sand filter just to guide the seepage line rather than going through the body of the dam, which is piping failure. You just put here just safe exit to make safe exit of the seepage flow to this direction simply. So you have this is just a drawing. So you have this is X and Y. X direction to this direction, you plot this phreatic line up to this point. So X to this direction, Y to this direction. So once you put this X and Y, you have directrix. So directrix. So this is directrix, a line which is parallel to the Y axis, to the vertical line. So from parabola property, you know, just the distance from the vertical line to the directrix and the distance from the focus. This is principal focus to any point of the parabola. For example, PO must be equal to PR, or PF, this is PF to this point equal to PR. So plot the various points P on the parabola in such a way that PF must be equal to PR. So if you substitute this equation, so PF means this one, this is PF, hypotenuse. So you have this triangle, this triangular portion. So just x square plus y square. X distance to this direction, y distance to this direction must be equal to x plus y naught. X distance plus y naught. So this is according to property of parabola. So the distance from the principal, from the focus to any point on the parabola, curve, to any point must be equal to from that point to the directrix, which is PR. So PF is equal to PR. So using that, just you will plot various points, then finally you can calculate. So from known point of A, once A point, this point is known, which is 0.3 L, because upstream slope and downstream slope of embankment dam known. So you know this point. Then finally, X is equal to B and Y is equal to H. These are known. B distance to this direction up to this point, then H distance, height. So once you know this, the rest you can calculate. Now let us calculate. From the above equation, just you substitute in place of X and Y, B square plus H square minus B. So why not? You will get this equation. So from this equation of parabola, once you put X square plus Y square, which is PF, is equal to PR, X plus Y naught, then from this you can find finally equation of parabola, which is this equation. You will get this equation. Finally, you can substitute. So discharge through the body of earth dam. So just Darcy for porous media will be valid using this equation. Velocity through porous media is equal to hydraulic conductivity times hydraulic gradient, which is I. So discharge intensity is equal to velocity times area. So KIA. So KI is substitute in place of velocity KIA. So this is the discharge through porous media in embankment dam. So once you have Q, just I means hydraulic gradient. Hydraulic gradient to any point, dy over dx times y. If you just make a simple rectangular portion through porous media, when flow is going, so perpendicular to the flow direction, you will find. So dy by dx times y. Y distance to the other side, then you have dy, the rate at which the depth is changing with respect to x times y, 1 meter. 1 meter width you just take for 1 meter width of the dam. So you substitute simply Q is equal to D times this one, dy. Y means this one, this equation. So if you substitute, if you derivate with respect to x, then you will get this equation. Then finally, hence we get this one, K times I times A, area. So we substitute, then finally this cancel, then you get this equation. So please just keep in mind that partial derivative and total derivative. So if you, this is just total derivative with respect to x. So d this function with respect to x. So just you derivate the variable with x, but the other variable keep constant. So y square simply you take. But this is 2x y naught. X you have, so 1, 2 times 2x times y naught. So 2y naught. So this is 2y naught. The rest without x, it will be 0. See, but this is 2x. 2x, x is 1, 2y naught. It remains. So like that, then cancel. Then to cancel, then you get ky naught. So this is the discharge through the body of earth dam. So this is an example. I think we will have an example problem. You can keep in mind, you will try. So for the following cross-sectional view of earthen dam, draw the seepage line and determine the amount of discharge that passes through the body of the dam. Assume coefficient of permeability or hydraulic conductivity 5 times 10 to the power of -6 meters per second. So you have dimension. Then finally, the first step is you have to get this point 0.3 times L. First, from this point up to the hill of the dam already given 58.5. So 0.3 of this you can find. Then finally, by substitution, you can arrive at the solution. Okay, this is the seepage line. Okay, phreatic line for a dam with no filter. If you don't have a horizontal filter, it will go like this. It will go like this. It will go through the slope, downstream slope of the dam. But actual phreatic line, it starts 0.3 L, then it will go like this. So you have change in A and A distance. So you make this is just alpha, A cos alpha to this direction, and A sin alpha to the above direction. Then finally you can find. So you will have delta A, which is correction factor. So just y naught, which is the distance from the vertical axis to the directrix, y naught you have. So as usual, you can just see. So this is just homogeneous dam with no horizontal drainage filter at downstream side. So the focus in this case will be the lowest point F on the downstream slope, which is on the top of the dam, but previously on the starting point of the filter on the above. On this one, the principal focus is just on the initial point of the filter. Okay, so let us see general solution by Casagrande. So the correction delta A by which the parabola is to be shifted downward. It will be shifted, you see? This is just shifting to this direction. So this is delta A, let us see, correction found by the value delta A over A plus change in A, value found from table. So alpha is just inclination of the dam. Downstream inclination is this alpha. Once you know, then you can find the ratio. So these are the ratios. So A plus change in A plus change in A from the above. A is this one, plus change in A means KF up to this dimension. So I think from this you can find. So discharge through the body of earth dam for alpha, if downstream inclination is less than 30 degrees, you can use this equation, which is Q is equal to K times A sin alpha tan alpha, and A is B over cos alpha minus square root of B square over cos square alpha minus H square over sin square alpha. You can use this equation. I think the proof is already given in the lecture note in the handout. You can refer it. I think very simple because it is homogeneous earthen dam. So for 30 degree less than alpha less than 60 degree, again you will use this equation. So A is will be calculated using this equation, I think, if it is in between 30 to 60 degree. Okay, phreatic line for homogeneous earth dam with rock toe. If you have rock toe, it will go to the rock toe, you see? So this is alpha. between the rock inclination and the horizontal base of the dam. So this is a phreatic line, but the actual phreatic line, it will start like this, then it will join. So vertical line. At this point, you can put discharge phase you have. So this is a rock top. So Fj is equal to Fj is equal to A, then Fk A plus change in A. So phreatic line for zoned as a dam with central core. Central core. If you have clay core at the center of the dam, this is like this. It will go like this. You see, like this. So you have dielectrics here, downstream shell and rock top. Then like that, it will proceed. Okay, so graphical determination of flow net. After having located phreatic line in earth dam, the flow net can be plotted by trial and error by observing the following properties of flow net, which means just the level below this phreatic line all just saturated. So you will draw like this. You will draw like this. So flow channel and flow equipotential lines. So you have a flow net. So using flow net characteristics, you can find the discharge. So each flow channel, then you sum up finally to get total. Okay. So I think next one is embankment dam construction, just to show you a picture which is just sloping. This is upstream sloping, which is Gilgil 1 hydropower rockfield dam with upstream asphalt. So asphalt is just constructing in this upstream phase. You can see this is. So I think once you complete, you can get like this. This is parapet wall at the crest of the dam. You may go vehicles going, so you have to put a parapet wall. So this is upstream wall. So this is a reservoir. So I think construction is just going, just from upstream to downstream, you compact, just for bondage. So that's why the asphalt is taking in embankment dam, so that just wave action will be minimized. Okay, stability analysis. So this is the next topic, which is stability analysis are generally needed under the following four conditions. So slope stability in embankment dams. So you have stability analysis of downstream slope during steady seepage. So when you have a steady seepage through the body of the dam, you will have downstream slope. You will do. Otherwise, stability of upstream slope during sudden drawdown. If the water level is fluctuated very fast, then you may have drawdown. Automatic, the level is decreased, then just the slope may be affected, which is upstream. Otherwise, stability of upstream and downstream slope during and immediately after construction. So during construction and immediately after construction, due to compaction problem and slope problem, then you may have slope problem. So stability you have to do during and after construction. So the other one is stability of foundation against shear just at the base contact. Okay, so you have Swedish circle method of slope stability, the first one. So in this method, the potential surface is assumed to be cylindrical, which is one section to be cylindrical, and the factor of safety against sliding is defined as the ratio of average shear strengths on that portion as determined by Columbus equation. So for the entire slip AB, we have driving moment and resisting moments. Let me show you. I will come back. So this is just the slope. This is the slope. So you have this is arc length and radius. This is radius and this is arc length. So you take this is assumed to be cylindrical portion. So you have base width is B and height. Then you have area. So we will see. So for a single, you can take now. Just you have for water pressure just going to the upward direction and normal force. So weight of this portion you have to this direction, and normal you have T no you have. So T is driving. This is normal. Just rather than going or affecting shear, just it will take to the downward direction, which is normal. So this is resisting. This is driving. So you have what? This is for water pressure. So where N is W cos theta and T is W sin theta. So you will use this equation for calculation. where n is just gamma times v, gamma times area, gamma times b times 1 meter width. So this is unit weight of the soil times cos theta you can use. Let me go back again. So driving moment is just radius times summation of t. Summation of t. So you have the radius, this one is radius, then summation of all t for the whole slip circle AB, this is slip circle, then you will get driving moment, and resisting moment, which is resistance cohesion. You have summation of change in L. Each slice you have width, then summation of arc lengths, then tan phi times normal. So this is the resisting moment. So where sigma t is sum of tangential components, sum of all normal components. Normal is resisting rather than going sliding, then it will rather than collapsing, it will take to the downward direction. So this is arc length 2 pi r sigma over 360 degree. So length AB slip circle. This is arc length. Sigma is the central angle. You can see now. This is sigma central angle of the slip circle. This is slip circle. So you have total factor of safety you will calculate now, which is the resisting moment divided by driving moment, where resisting moment is cohesion times length, which is total arc length, and tan phi, which is the angle of internal friction of the field material, times normal force over summation of t, which is driving force. So shear strength available over shear strength required for stability, you will divide. Then factor of safety must be more than 1.5. Okay, so this is just method of locating center of critical slip you have. So you have slope, for example. Let us see. This is just if you have upstream slope, then you draw a line. So how do you make locating center of critical slip circle? Let us see. Like this, you draw like this. So this is the first one, location of slip surface. Once you put the foundation, which is to this direction, 4.5 h. H is the height of the dam. Then FS1. So this is a factor of safety 1. Again, you start again another. You draw. This is factor of safety second. And this is just the third, etc. It goes on like that. So once you calculate this one, then you will select the best factor of safety. So stability of downstream slope during steady seepage, you can have downstream seepage condition. If seepage is continuously flowing, this downstream will be in danger, so it may collapse. So I think you have like this. Then each slice you can draw the free body diagram. Then finally you will do factor of safety is using this equation. Critical condition for downstream slope occurs when the reservoir is full and percolation is at its maximum rate. So the directions of seepage forces tend to decrease the stability. So this is important. So factor of safety is cohesion times length of the slip circle, plus tan phi, sum of normal minus u. If you have poor water pressure, you have to subtract. Normal is to the downward direction, and this u is to the upward direction. So you have to subtract or divide by this is summation of t, which is driving force. So in the absence of a flow net, you can use this equation, which is factor of safety of downstream slope can approximately be from the equation, this one, which is effective normal force, which is you may have submerged unit weight, etc. You can apply. So the following unit weights may be used for the calculation of the factor of safety, and when poor water pressure are otherwise not included in the stability. However, the Phreatic lines need to be drawn. So you have, for example, location. If it is below Phreatic line, below Phreatic surface, driving force, you will take driving force, which is T, and resisting force N. N means W cos theta. This is T means W sin theta, as in the previous free body diagram for a single slip surface, which is for a cylindrical unit. And above Phreatic line, moist unit weight, and moist unit weight you will take. So saturated, submerged unit weight, moist unit weight, and moist unit weight you will take. So this is an exercise. I think it is included in your tutorial exercise. Then you will try. And you have above and below phreatic line area given. This is a drawing. So you have, if the phreatic, this is a phreatic line. If it is fully above, you will take above from the table, from this table, above phreatic line, moist unit weight for driving force and moist unit weight for resisting force. So when you take W sine theta and W cos theta, you should go to gamma times volume in place of W. So gamma you will select from this table, whether saturated, moist, or submerged, etc. So I think this is a good example you have in the worksheet problem. So I think the next topic is chapter 3, which is dam outlet works. I think we shall stop here. We will have illustrative example on embankment dam with filter and without filter, and also slope stability for sudden drawdown and also steady seepage condition, downstream and upstream slope. Okay, thank you. And thanks for watching this video. So this is all about today's lecture. Hopefully you liked the video. If you have any comment or question regarding this topic, please write down in the comment section below. I will reply on it. Please like, share, and subscribe this video to get more precise lectures. Thanks.